Okay, so hello everyone. We are from Craftinity, a startup based in Krakow. We mostly work on computer vision tasks, sometimes some natural language processing. And today we talk a little bit about image segmentation, which is actually one of our most, which is one of the areas we are most interested in computer vision right now. Okay, so here is some short plan of our presentation. So at the beginning we talk about segmentation in computer vision in general. Then we skip to deep learning methods for image segmentation, and we'll present case study based on clothing parsing. So let's begin with segmentation in computer vision. So in computer vision we can define three general tasks. The first one, classification. So in classification we want to assign a label to an image, so we call it image level annotation. So we have just the information that somewhere in the image is address or heels or back or whatever, but we don't know where, and especially we don't have any segments of that, on any shapes or something like that. And the other one, which is a little bit more difficult, is object detection. So we have usually tight bounding boxes which are around objects we want to predict, we want to detect. And the third task is segmentation. In segmentation we want to assign a label to each pixel on the image. So we have these pixel-wise annotations, and it can be very helpful for do some image search or color detection with good performance. So these three of these are three basic, maybe not basic, but general tasks in computer vision, and usually on challenges like ImageNet we have competitions for all of them. So semantic segmentation, in terms of segmentation we can differentiate two kinds of segmentation. The first one is semantic. So in semantic segmentation we just want to annotate each pixel on the image, but we don't differentiate instances of some objects. So on the first image on the left where we have cows, we don't know how many, and for some applications we would like to know, so it's not enough to do semantic segmentation, but for some applications it's okay. So the other segmentation task is instance-aware segmentation, and it was recently introduced to MS Coco Challenge in 2015 because probably semantic segmentation at some point started to have really good results, and we needed some better challenge. And instance-aware segmentation sometimes is called simultaneous detection and segmentation, because we detect all of these instances and we want to segment them and assign each pixel a label to each pixel. So before deep learning, back to 2012 probably, in segmentation, we have some traditional methods, and this is a pipeline from paper doll parsing paper. So the problem they were trying to solve was clothing parsing. So they wanted to label each pixel on an image where was some model to some set of categories which were some basic clothing items like shoes, or maybe not so basic, like if you differentiate between shoes and you got boots or heels or something like that. So you can see that this pipeline was quite complicated. At the beginning they were doing some pose detection to set up some better priors. They were doing some style retrieval based on some computer vision classic features like histogram of oriented gradients or maximum filter responses. And then they were doing just parsing on those features with some logistic regressions and some iterative smoothing. And first of all, it was not so good. This method has 0.4 something like that f-score for segmentation in average. And the second thing, it's not end-to-end training, so it's quite hard to train. It's complicated framework, and definitely that's not the goal, and that's not the way we want to do the segmentation. So after 2012, and especially after winning ImageNet in classification task by AlexNet, deep learning methods aroused and become the first choice for computer vision tasks. So there were some starting methods for image segmentation. So basically in deep learning, in terms of computer vision, convolutional neural network is some kind of like basic building block, and we have many different architectures, and probably everybody already heard about GoogleNet or VGG or residual networks. And convolutional neural networks is a net which comprises of convolutions and pooling and sometimes some fully connected layers. And in all methods we will present today its main building block, and we can use it just as a black box. Okay, so the simplest way to replace that horrendously complicated pipeline from clothing parsing is to extract some patches from the image, and on each patch we want to label a center of an image. And after that we have some response that we have a dress in the center of this image, and we can repeat this for each pixel on an image, so we can get a segmentation mask. So during training it's not so infeasible, because we can just sample from big data sets some small subset of pixels, and usually it's important to have uniform distribution in image of all labels. And the training works quite well, and it's a little bit better than those traditional pipelines. But there is a big problem in the test time, because you want to predict each pixel, a label for each pixel. There are so many pixels, and it's really time consuming. So what can we do? So the basic idea is to just put a whole image into the net, and when we have those fully connected layers in convolutional neural net, we can treat them as convolutional layers with 1 by 1 filter size, and that's the same. So when we treat those way, these convolutional fully connected layers in convolutional neural net, then we can just feed whole image to the net, and we get the output with segmentation mask, but much smaller than the input size due to pooling and convolutions also. So that's a problem, and if we want to go back to the original size, we need to do some upsampling. And some arbitrary upsampling probably it's not the best idea, but this way it was done like in 2013, I guess. But in 2015 there was this quite good idea to learn how we can upsample those feature maps. And it was presented in the paper Fully Convolutional Networks for Semantic Segmentation. So the architecture is basically some convolutional neural net, probably it was AlexNet here. And after last layer, we do upsampling with deconvolution operation. And we'll talk about it in a minute. So let's, for a second, just assume that everybody knows how deconvolution works. And we have this AlexNet architecture, and we do upsampling of feature map from different sizes of feature maps in the net, and then we can aggregate those upsamples, and actually it occurs that the results after this aggregation from different levels of the neural net are better than just upsampling the last layer. And actually the motivation is the last layers usually keep semantic in neural nets. They are very good in semantics, but they are not so good in localization or local patterns or some edges and so on. So if we want good localization, we should somehow use the layers which are at the beginning or in the middle. So these are the results from example results from fully convolutional neural net paper. So we have a ground truth, which is the correct annotation made by human, and FCN 32 are just results from the last layer. Then we have the result from 2 last layers and 3 last layers, and we can see that those results are becoming more and more sharper and more smooth, actually just better. So the main contribution of this paper is learnable upsampling, which is called deconvolution, and probably this is a misleading name because in signal theory deconvolution is already defined as inverse of convolution, and it's quite a different thing, and it's probably more appropriate to call it transpose convolution, but already in machine learning we have many papers that call it deconvolution, so it's just something what researchers can quarrel about. So typical 3x3 convolution with stride 1 and pad 1. So we have some input feature map or channel, and let's say it's 4x4, and with stride 1 and pad 1 and 3x3 filter we will get output of the same size. So it works like we have some filter, we are going with sliding window through the input image, and we are doing just dot product of the filter and the image, and we put the result into output, and it's just the next blue one, and we got the second score. So in case of stride 2, we go with sliding window with the step of 2, so we are decreasing with the size of output this way. Okay, so the next thing is deconvolution. So actually deconvolution is just a backward pass in the backpropagation for convolution. So it's very easy to implement this because it's already implemented everywhere when we want to do a backpropagation and learning with some gradient descent method. So basically we have some input of 2x2 and we are doing 3x3 convolution with stride 2 and pad 1. So we have some score, and input gives a weight for a filter, so it's basically just multiplicating a filter and putting those results into output, and then we have a second weight for this filter, and where those outputs overlaps we just sum, and that's all deconvolution. And this way we can learn these weights for upsampling, and we can upsample better than just in some arbitrary way from OpenCV. So the next step was to introduce more deconvolutions. Usually the next step in deep learning is more and more layers, going deeper and deeper, and adding some more good stuff. So here we are adding more deconvolutions, and actually we are just doing upside down VGG or upside down convolutional neural net. So here we have VGG net, which was from 2014, and it won ImageNet, I guess, at that year in classification and object detection. So it was a 19-layer network, and yeah, it comprises of convolution and max pooling operations. And they just added, after the end of VGG, they added upside down VGG, so all of those operations but reversed. So we have some unpooling operation, which we talk in a minute, and deconvolutions to replace convolutions. And this net was a little bit better than just those fully connected with one deconvolution. So pooling is the other main operation in convolutional neural networks aside of convolution. So pooling is just going with some window through the input and taking some score, usually maximum from this red square, and putting this into the pooled map. So this operation is for decreasing the feature map size, and actually there are two reasons to the pooling. The first one is we want to decrease those feature maps because then it's less time consuming to compute the forward operations for the net. And the other is pooling introduces local invariance to translations, which is very important for us. So So we are just taking this maximum, so this blue box into the pool map, and we remember we've switched variables from where it was, so we can do later unpooling. When we have some pooled map, we know where we should put those value, and all of others value in this red rectangle are just 0. So we lose some information, but at least we put this value from pooled map into the correct spot. Okay, so here are some results of comparison of DeConvNet. So this is this upside down VGG with VGG, and fully connected convolution.net with just one layer of upsampling. And the first two rows show example where DeConvNet is quite better than fully connected. So the first column is input, the second is ground truth, so annotation by human. This third is fully connected convolution.net. The fourth is just DeConvNet, and then we have some ensemble of DeConvNet, so the set of couple networks. So they are usually better than just one. And the last one has also some conditional random field post-processing, and we'll talk about it later, how it's done and why it's important. And in the third row we have just actually example where FCN is actually better than the DeConvNet, so it can also happen. So those operations, deconvolutions and our pooling and those networks were very important for this task and the development of better methods in deep learning, and they are kind of building blocks for new state-of-the-art methods. And now we'll talk about the method which was state-of-the-art till I guess June, but everything happens very quickly here, so it's not.
Okay, let me say something about the model which was published in the paper made by the Deeplab group. Let's call the model Deeplab for short. And Deeplab is a combination of CNN, obviously, and two other operations. That is the post-processing step with conditional random fields, and Atrous convolution, modification of the standard convolution, which is obviously a part of the CNN. Before we dive deeper into these two operations, let's see how it works. At first, the input is passed to the CNN model, and the CNN outputs the so-called score map, which has spatial dimensions decreased 8 times, and the size of the depth channel is equal to number of classes we'd like to detect. And later, this score map is bilinearly upsampled with the factor of 8 to the original resolution. Bilinear interpolation is just an example of fixed upsampling. It doesn't have any parameters like the convolution, and this interpolated score map is later passed to fully connected conditional random field, which post processes it and outputs the final prediction. Okay, and let me say something about the conditional random field. In general, it's a broad topic, so we don't have time to cover it here. But a few words may be sufficient. There's a probabilistic graphical model which models the conditional probability distribution of some group of variables given another group of variables. So in our case of segmentation, it models the probability of label variables, label of pixels, given our image, given our pixels. If we think about what we would like to model, that's exactly a distribution which we would like to compute. And in order to compute this, we need to we need two quantities. The first is so-called unary potential, and the second one is pairwise potential. One may ask how this CRF interacts with CNN, and it's happened that CNN provides us with unary potentials. So we've got the first ingredient to compute the distribution, and second, the pairwise potential is just an expression of two label variables, which is quite similar to the functional form of normal distribution. Because unfortunately, computing this distribution P of x given I is intractable, we need to rely on some kind of approximation algorithm. And luckily in 2011, some researchers from Germany published the approximation algorithm, which is pretty fast and is quite accurate. So the post-processing using this CRF in image segmentation may be feasible now. Okay, so let's say about something about the Atrous convolution. The Atrous convolution is called also a convolution with faults. What's the difference between the standard version of the convolution? In standard convolution, when we take the input and convolve it with the filter, we take the input continuously. But in version with holes, we make some skips. So we take every second, every third or every fourth cell of the input, and how much do we skip is controlled by the rate parameter. And what it gives us the first we can there's another parameter which enables us to control the output size of the feature map, the output of this convolution. And second, it allows us to enlarge the field of view without sacrificing too much of the performance, because the convolution with holes is not in terms of performance is comparable to the standard convolution, because we don't take the half of the input or the third of the input. Okay. In the paper published by Deeplab, there's also a little interesting experiment attached. Let me describe it. This is the typical situation in convolutional nets where we perform the convolution on the input, which was formerly decreased in size of spatial dimension, and later we often need to upsample the input, for instance, to make the pixel-wise prediction. And in this upper branch, we take the input, we downsample it with the factor of 2, later perform the standard convolution, we have some output feature map, and later we upsample it with the factor of 2, and in this output we can see that there are some holes. That's because we have only a fourth fraction of values compared to the original input. And in second branch, there's a Atrous convolution performed on the input, and it's performed on the input which is not downsampled. And as a result, we can see that we have the output which has a better quality, so to speak, compared to the output above it. And what's important to mention is that the computational time is not much higher than the standard convolution. So I think that's quite nice experiment. Okay, and that would be everything about the theoretical part of image segmentation with deep learning techniques. And let us present our case study with semantic segmentation. Okay, so our domain is a set of images coming from fashion industry, and we need to predict masks for some more important categories like dresses, bags, shoes, trousers on it, and we'd like to have this mask to be precise. For instance, to be able to further work with these masks that may be useful for instance, for image search. And the biggest publicly available data set which contains images with ground truth labels, labels coming from fashion industry, contains 7.7 images. So it's our setup. And this data set, this biggest data set, is called ATR data set, and that's the example of the image with ground truth. This ground truth is just a mask where every pixel has a label assigned. This data set contains 18 labels. 18 categories, sorry, and these categories are mostly part of clothing. So that's why I use it, because it's the domain we are working in. The next few examples. Okay, so we attempted to solve this task with two different methods. The first one is straightforward. It's just to perform a general segmentation. It's just to take a model, a deep learning model like Deeplab or FCN mentioned by Matthew, and just do the segmentation and fetch and grab those masks for categories which we are interested in. So we decided to take the Deeplab. It's based on VGG16 architecture. We decided to try it with either including CRF post-processing step and without it. When it comes to technical details, we fine-tuned this model from VGG16 model trained on ImageNet classification challenge, and we pass the image. We pass to the network images with 500 on 500 in resolution images. And when it comes to training details, we took the batch size equal to 8. We perform only 10 epochs, and we divided whole our data set, that's almost 8,000 images, into train and test mode with the ratio 0.9. Okay, and here we have our results. At first, let's verify it visually. So in the left upper corner we have the input image. On the right we have the ground truth mask, which is included in this ATR dataset. And on the bottom there starts our prediction. So the left model is the Deeplab without CRF post-processing, and on the right it's the model with the CRF post-processing. And as you can see, this model performs quite well on this image. But when it comes to differences between the model with and without CRF, we can see that CRF gives us the masks which are a little bit sharpened compared to the standard Deeplab model. we also see that we lost the differentiation between right and left shoe. But in general, that's a well-known effect of CRF post-processing, that these outputs tend to be more sharpened, while without it, these predictions are more blobby, so to speak. Okay, and next example. As you can see, with CRF, this hair are predicted with more details. Okay, but that's about visualization, but it's better to take a look at the numbers. So we measured the performance with 5 metrics. That is accuracy, precision, recall, F1 score, and intersection over union. We did it for 2 categories, bags and dresses. If someone knows something about measuring the performance of classification, these 4 first metrics, that's accuracy, precision, recall, and F1 score, are familiar. And it's quite natural to apply these metrics in the segmentation task, because what we are doing here is we are classifying every pixel. So segmentation is just the classification of every pixel, and we can apply the metrics from we can borrow metrics from classification. And when it comes to intersection over union, it's just the number which says which gives us information how much the 2 masks overlap. So it's bounded by 0 and 1. So 1 is a good result, 0 not. And when comparing the Deeplab model with and without CRF, we can see that Deeplab with CRF post-processing has a slightly better metrics. I think that in case of segmentation, the intersection over union is the most representative metric, so it's worth to take a look at it. And the same rule applies to dresses. Deeplab with CRF is also better. It's even the gain is even better. It's 5%. Okay. Okay, that would be everything enough about our first method. But our second attempt consists of detecting the object on the image, so detecting the rectangle which surrounds the object of given category, and later do the segmentation around this bounding box. The segmentation in, sorry, not around bounding box, in the bounding box. In this bounding box, the segmentation is just a simple foreground-background extraction. So it can be any model. It can be a deep learning model like Deeplab, with trained only on 2 categories, foreground and background, or it can be, any another algorithm like GrabCAD. So our small pipeline here is as follows. As first, we have the detector, which detects the bounding box of the object. It can be any. We can apply any detector like faster RCNN, SSD, YOLO, and later, as I said, we do the foreground-background extraction. And our hypothesis here is that if we have an exact bounding box around the object, performing the segmentation in this bounding boxes should be much easier than do the general segmentation, than trying to detect the mask for the category from the whole image. And because we decided to use the SSD detector because first it's working it works pretty fast. Second, it's not so hard to train, contrary to, for instance, faster RCNN. And what's more, there's a cafe framework branch available on GitHub, and it's not so difficult to adopt this model to your own dataset. So we use the SSD detector, and only a few words about how it works. SSD extends the VGG16 architecture, so it takes the most of the convolutional and pooling layers, but after that it adds some convolutional layers which goal is to discretize somehow the space of possible bounding boxes, and with each cell of this convolutional feature maps there's associated a small number of predefined bounding boxes. It's usually 4 to 6, and this every cell tries to predict the offset of the bounding box for each category, as well as the score for the category. That is the confidence that in this region, which belongs to this particular cell of this convolutional feature map, that it contains any object. But let's treat it as a black box, which simply takes an image and outputs the bounding box with confidence that it contains an object of given category. Okay, so for each category, we trained a separate SSD detector. So in case of bags, our dataset contained almost 4,500 images. In case of dresses, this dataset was bigger. It was almost 15,000 images. And in detection, we measure the performance with mean average precision, and in case of bags, this SSD detector was much better than in case of dresses. These numbers are relevant to the final result of segmentation, which we perform with using this second method, with using this pipeline of detection and segmentation. Okay, so let's take a look at the performance of this pipeline on bags category. We copied the results from Deeplab and here to compare it with this the second method. DNS means detection segmentation. So it's clear that in terms of IOU, this performance is much better than these two methods. And that's mainly because, the detection of bags very accurate, which is apparent from the previous slides. The mean average precision of on the level of 93% is a really great result. But when we take a look at the dresses performance, it's actually the performance of detection and segmentation is somehow between the Deeplab without CRF and with CRF, and it's mainly because the detection on dresses is much less accurate than on the bags. Okay, and finally a visualization of this our second approach. That is, we detect the bounding box around the bag, for instance, and later segment it with a Deeplab trained on two categories. So that's how the mask looks like. And that's the example for dress. As we can see this on this image, this segmentation is really accurate. it's not on every image. Obviously, this mask is so accurate, but we included only the nice one. Okay, let's go back. Okay, and finally, some information about our tools. So for every type of task we presented here, we use the Cafe framework with Python. For SSD, we use the branch of Cafe, which lies on the URL. And finally, for Deeplab segmentation, we also use the Cafe version published by the authors of this method. Okay, that would be everything. If you have any questions, feel free to ask. Thanks for attention.
We have space for one question. Today, unfortunately, we're very packed with talks, so we don't want to finish after 10 with our speakers. So, okay, we have one question.
Thank you for your interesting talk. I have a question about the term of convolutional neural network. Is it a broad, general term, or is it only an architecture of neural network designed specifically for the problem of image segmentation? And if it is not, do you know any other applications of this kind of method?
Convolution is the operation from the signal processing domain. So it means to perform some kind of dot product between the signal and between some input. So it has a quite general meaning, but in terms of but when it comes to convolutional neural nets, it's just a network which performs the operation of convolution. So when it comes to convolutional neural network, it's a strictly neural network terms.
Yeah, it's strictly neural network terms, and you can apply it to many other areas. So you can do sentiment analysis because you can go with the sliding window through the text, through some context. And it's a very common way to do sentiment analysis. And the other interesting thing is, recently there was published WaveNet paper from DeepMind, and they actually, I'm not sure if it was speech detection or but some work on speech, they use convolution. Yeah, text to speech, exactly. Yeah, they use convolutional neural nets with some tricks. Yeah.
Yeah.
Okay, thank you so much, guys. So, applause please once again. Thank you for coming.